Hello guys, in this video we will see how to simulate a flow over prism in OpenFOAM. So this will be a steady state case and we are going to use OpenFOAM. For geometry preparation we will be using SolidWorks, and for meshing we will be using ANSYS. So we will also see how to use ANSYS mesh inside OpenFOAM. So this is a steady state simulation, so only the final time step where the solution is converged is useful, but still in OpenFOAM we will get a simulation of all the test case which can be seen like this. So this is the simulation over all the time steps where the solution was made. So in the final result, that is in this case, we are having the final steady state flow over the prism. So we will see how to make this geometry. For making the geometry, I am going to take SolidWorks. In the SolidWorks, I am going to open the front plane. In the front plane, I am going to take polygon, and in the parameters I'll choose 3 since we want a prism. So I'll just draw a random triangle, and in the units make sure that it is in meters because in this case I'm going to take meters. I'll give edit sketch and make sure that this is vertical if you don't want any attack angle, so that it will be normal to the flow. If you want any attack angle, you can just specify over there, and I will make this as construction. So you will know why I'm doing this later. So I will give this as 1 meter. So this is a equilateral triangle with 1 meter. So in this case we are going to deal with 2D instead of 3D. So we will see how to do it. And I'm going to take a corner rectangle from here to here approximately. So I'm going to specify the dimensions. So if you see this rectangle is the enclosure or the flow domain where the fluid will be there. So I am going to specify some constraints. I'll make this point horizontal to this point, and let this dimension be around 6 meters, and let this be around 12 meters, and I am going to make this as 4 meters because we want some space for the flow to develop so that it can be slightly parabolic before it starts to hit on the prism. Otherwise it will be very linear because we are going to give linear velocity inlet instead of parabolic. So this will be useful for the flow to develop before it reaches the prism. So I'll make this rectangle also for construction. You will know why I'm doing this. So we are going to make a structured grid, not a perfect structure grid, but we are going to make it as blocks. So I'm going to take the front plane, and first of all I'm going to make this square, and square or rectangle, and I'm going to extrude it. Here the extrusion length doesn't matter because we are going to do 2D case anyways, but I'm going to keep this as such, and let this be 0.01. The only thing is it has to be uniform for all this stuff. So I'm going to click on OK. Again I will go to front plane. So I am again going to front plane, and I am drawing this, that is here to here, vertically here to here and here, and this is one space which is covering the uh, triangle, that is a prism, and I'm going to extrude again, but make sure that this merge result is not checked in, only then we will get a different bodies. So I'll check on this. Again in the front plane I'll choose this, and from here to here I'm drawing a rectangle. Again I am extruding it, and again I am not going to merge the result. I'll click on OK. So since we have created half of the body, we can just mirror it. For that I am going to click on mirror, and the mirror plane has to be top plane because you can see the visualization. Only if we mirror on the top plane we'll get a symmetric body. And in the features I'm going to go to bodies, and I'm going to select all 3 of these bodies so that I will get a mirror of the bodies. I'll check on this, and if you see there are about 6 bodies, which are this and these 3. So the only space left is here, and I'll go to front plane and draw this rectangle too. So I'll just draw this and extrude it again and make sure not to check on the merge result. and click. So I can hide the sketch now, and if you can see, we have the prism, and we have made multi blocks of the domain flow domain so that the mesh generation is easier and it is more clean. Now for this geometry, I have to import into ANSYS, so we have to save it in that file format. So I am going to save as I'm going to already I have a folder. Around that I have saved the geometry as geom, which is in the SLDPRT format, and I'll just save it. And again I'll go to save as and save it as IGS format. So IGS format is a format which can be imported inside ANSYS. So I'll give Geom2 because I have already done an IGS file. But if you want, when you're doing first, you can save it in any name you want to. That is not a problem. And you just make sure it is in IGS format. I'm going to give save. Now I will move on to Workbench. In the Workbench, I need not import Fluent or anything. If you go to component system, sometimes it will be hidden. So in that case, you can just open it. Sorry, this one. In the component systems, you can just import mesh, and in the geometry, right click on this and give it as import geometry, and browse to the folder where you have the IGS file and select on this and give open. After that, make sure that it has a tick mark, or else again you have to do it. Left click on this, and on the right panel there will be an option called 3D. Click on that and make sure you are selecting 2D so that the geometry is taken to the mesh as a 2D. I'll right click on this and open in design modeler. Wait for some time till it loads and click on generate. Now you can see that we are having totally 7 bodies, and here if you want to have it as add frozen, you can have it, or if you want to see it as add material, you can just do it. It is not a problem. And once you go in here, what you have to do is select all of these, and you can see in the fluid or solid option it is given as solid, but you have to make it as fluid. Only then these bodies will be considered as fluid domain. Now click on generate again and make sure everything is fluid. You can select on all of these and see if it is fluid or not. Even if you want, you can select each one of these separately and see if it is fluid or not. After you do that, we have to create faces. So since we extruded towards the positive z-axis, this plane is what is there in the origin, that is the back side. So when you see from isometric, this is the front, and this is the plane which is the actual front plane. So what we are going to do is we are going to go to the negative z-axis and click on concept, surface from faces, and I'm going to select each of them and click on generate. So you have to do this for all the faces so that we are getting only the surface, so that we can do 2D case, otherwise it will be a 3D case. So you just have to do it for all the 7 faces. Doesn't matter in what order you are doing, just make sure that you are selecting all the 7 faces. Okay, once you have done all the 7 faces, or in this case I have done only 6, so I want to know which face I missed, so I can just suppress this body and see which face I have missed. It is this body, so I'll unsuppress again, and I'll insert this. Now you can see that I have all the 7 bodies. Now I will hide all the solid ones so that we will have only the surface bodies. So make sure that it is all 2D as well as it is fluid. So if it is solid, the simulation is not going to run. So make sure it is fluid. And after it comes like this, you have to select all these, that is the 14 parts and 14 bodies you can see. So we have to select all the 14 bodies, right click on this, and you have to give form new part. So once you do that, you will see that there are 1 part and 14 bodies. This is very essential to make a uniform mesh within the boundaries of the bodies. If you see, these are the interfaces. So if the mesh has to connect properly in the interfaces, it has to be a single part. Different bodies doesn't matter. So there are two things that you have to check, that everything is in a single part. Also, all these solid bodies are suppressed, and also check that it is a fluid. So once you do this, you can just click on generate for once more, and you can close this. And now also you just make sure it is already in 2D. Now go to edit of the mesh. We are in the mesh workbench, so we just have to wait for some time till the geometry is loaded. Now you can see it has all the 7 bodies as 2D. And I will go here and change the physics preference to CFD, because the meshing for CFD is very much different than mechanical. So I'll change it. And if you have multi-cores CPU or multi-thread, you can change this or leave it in program controlled. I have 16 threads, so I'm going to take 16. I'm going to generate a default mesh, whatever is there. Now you can see it is very coarse. It is for 0.67 meters. I'm going to slightly decrease it to 0.5 to see how it goes. It is pretty good. So I'm going to go further down to 0.1, and you can see that it is taking slightly longer and the mesh is now finer, but there are some mesh which could be still finer because it has a flow domain over here in the trailing edge. So I'll make it further small to 0.07. It will take some more time, so it is advised to use multi-cores processors. Now if you see, it is still finer. If you have a very good computer or CPU, you can go still finer. I'm going to go to 0.05. If you don't have a very good processor, you can just leave it as such. Once the mesh is ready, we have to give the naming selections, which will directly get imported into OpenFOAM. So I am going to select this and this face, which will be right click, and you can select on create named selections. You can give it as inlet, and you can select this face, this face, this face, and press N or right click to give it as outlet. And everything else will be default as walls, but still I'm going to select and give it as walls. It is this this these three faces of the prism and these three. So I'm going to give it as walls. So it doesn't matter if you have upper wall differently or lower wall differently. I will talk about that once we are setting up the case file in OpenFOAM. Now we can check if the uh, naming selections are properly given. For inlet, we can see that this is the inlet and this is the outlet and this is the walls. So that is very clear. So we can just import this into OpenFOAM using few simple steps. So what I'm going to do is click on file, export, mesh, and inside this you have to click on fluent input file. You have to give export. Inside this I'm going to go to the folder which I want the file to be saved, and inside there I am going to save it using a name. For example, I'm going to use flow over prism mesh file, and make sure it is in the .msh format. Give it as save, and after you save that, you have to go to your OpenFOAM directory. That is, you have to create a folder. For example, I am using WSL Linux. If you are using a Linux standalone OS, or if you are using inside VirtualBox, you just have to create a folder inside home. Any name for your folder, and over there you have to take your terminal. So I'm going to open my WSL terminal. It is very convenient since I'm using ANSYS along with OpenFOAM, so I can use Windows and Linux parallelly without having to boot it separately. So I'm going to go into that folder. Um, so once I'm in this folder, I have to copy that file here. So for that, you can just use your normal Windows Explorer, Control C, and paste it over here, Control V. Okay, now we have to see what type of simulation we have to do. So I'm going to go to tutorials folder of the OpenFOAM installation directory. Usually it is in this path, that is directory, that is Ubuntu. Inside that, user, library, OpenFOAM, and OpenFOAM whatever version you are using. Inside that there is tutorials. Now for this case we are using a steady state simulation, so that I am going to take incompressible SimpleFOAM. So SimpleFOAM is a steady state solver, and it is the most widely used solver. So inside this, a pitch daily is a tutorial which is very similar to what we are doing. So I will just copy all the folders inside the dependency files, the zero, constant, and system. Make sure you are copying all of these three and paste it in the folder that you have created for your directory. So when I go into this, I have zero, constant, system, and the flow over prism mesh file. Now inside this WSL Linux, give ls to, so you can see that we have all these folders. And before that, if you see in the constant folder, there is no folder called polymesh. Now what I have to do is, there are two commands that I can use, that is fluent 3D mesh to whom, followed by the name. So when I do this, if it is a 3D mesh, the mesh will be converted into OpenFOAM readable format. But this is not a 3D file. This is a 2D mesh file. So I'll just remove this 3D. So it will be fluent mesh to foam followed by the mesh file.msh, and I will click on enter. So once you do this, there are two things that you can observe. First thing is the inlet, outlet, and walls. The namings have just got imported directly. And the other thing is there is front and back planes which are named as empty as a patch. If you see here, the inlet type is a patch, outlet is a patch, walls or patch, that we have given the naming. But front and back planes are not what we named, and it is given as empty. So what does it mean? If you see here, there is this line called dimension of the grid 2, but grid is 2D, so extruding it in the z direction by 0.26. So this is a standard methodology followed by OpenFOAM to make any 2D mesh into 3D mesh. So after it is converted into 3D, the 3D faces is defined as empty, so that it is not actually involved in the simulation, but it is there for its own convenience. So how to visualize it? I'll use touch para.foam. This will create a para view file inside the directory, and I will just open this. Inside this, I can click on apply to see that. I'll go to surface with edges. Now you can see there are not different bodies. It is of a single body with the mesh, and I will deselect the internal mesh, and I will show you what are the front and back planes. So once I click on this, you can see that there are two planes, but it is empty, which is meaning that it is not actually involved in the simulation, but it is just there for numerical convenience. So I can select on inlet and outlet. You can see that these two phases are inlet and outlet. Though it is 2D, it is taken as 3D for its convenience, and I will click on walls, and you can see that these are the walls, the upper, bottom, and the prism was considered also walls. And I'll just select the internal mesh now, so that we can get all the mesh files. So this is not needed as of now, I mean the para view, so I will close this. Now we can see how to modify the set of files. So I have said that it is going to be a 2D laminar steady state case. For steady state, we have copied this SimpleFOAM case. So for laminar, we have to change few things. Now you can see that polymesh is also available after we created. So inside the polymesh, there are boundaries, cell zone, faces, and everything. These describe the geometry which is readable in the OpenFOAM format. So inside transport properties, there is this constant, that is nu, which is the kinematic viscosity. The model is Newtonian, so there is a defined new kinematic viscosity, which is 1e minus 5. So how is this useful? You can just use it to calculate the Reynolds number using Vd by nu, where the d is the characteristics length here, that is 1 meter. So in the turbulence properties, if you go, there are Reynolds averaged simulation is used. So I said that this is going to be a laminar case, so we are not going to use RAS. Instead, I have to change it to laminar. So I just change it to laminar and save the file. Now I can go to the system, and the block mesh is something which will define the mesh file inside OpenFOAM, but here it is not needed since we imported the file from ANSYS. I'll delete this. Even if it is there, it doesn't matter. And streamlines are there for only incompressible flow, we know that. So since we are using incompressible simple form, streamlines is also there. So I can go inside this and remove this k, which is a turbulence model. So the k is not needed, only u and p is needed. And FV solution and FV scheme can be default, but if you want to open and see what are the solvers which are getting used, you can see the lesser the residual control value, the more accurate the solution is. But for this case, I'll just leave it in default. And these are the schemes which are getting used. You can read the documentation to know more about this. And in the control dict, we can change the time step, end time, and everything. Now in this case, I'm going to take right interval as 1, since this is a very simple case, and it could converge very faster. And the delta t is 1. So for every time step, the right interval, that is the animation, will be recorded. And start time is 0, end time is 2000. If this simulation converges sooner, it will not uh, go up to 2000, that is well known. And in the function, they are including the function of streamline. So if you don't want to calculate streamline, you can remove this function. So I'm just going to leave it as default as such. And if we go to 0 folder, we can see all these files. But since we are using laminar model, epsilon k, nu t, nu tilde, and omega is not needed, I'm going to delete these. Now I'll just open these two in Notepad++. You can also use Vim or VI. And in the U, you can see there is inlet, outlet, upper wall, lower wall, front and back. As we saw in the mesh, there are front and back planes, which is front and back. And for walls, there are actually two, upper wall and lower wall. So what we have to do is remove this, and we have to give only wall. So I'll remove this and change this as walls, and let it be no slip for the velocity. Meanwhile, I have also changed the value to 3e minus 4, since the Reynolds number could be slightly bigger, so that we can get a tail behind the prism when we plot the velocity. And for the pressure, we have to do the same thing, remove any one wall and rename it as walls. Let that be zero gradient, because the pressure at walls are zero gradient, and inlet is also zero gradient. Front and back is as usual empty, and outlet must be specified as a fixed value of uniform 0, so we are not going to change that. Now if you see that we have sorted out 0 folder and constant, we have changed the transport properties to laminar, and turbulence properties is set as such. And the system, we have not changed much except for the control dict. So we can just run this case. Now I can go to the folder where I have this. So after making sure that the folder is clean, you can just write in SimpleFOAM, and the simulation will start running. And after a few time, once the solution is converged, you will get a solution is converged like this. So the simple solution is converged in 95 iterations, and you can see the final residual has gone up to 10e minus 4 here and 10e minus 3 around here. So this is a good simulation, and it ran pretty fast. So since the number of cells are very less, and since it is also 2D case, it ran pretty fast. Now we can go to the folder, refresh it to see all the case files. Since we wrote the right interval as 1, we have all the files. Now I can open this case in ParaView. After I click on apply, this is a point based data, so I'll go to cell based data to see the pressure. If I go to the last time step and rescale to the visible values, you can see this type of plot where the pressure is very low at this point and it is very high over this point. And if I go to velocity, we can see that the solution is converged. After this, it is very steady state, the flow is not changing. But if you want to visualize it, you can press on this button, so we can see how the simulation propagated to reach the steady state. Um, so this is the last time step over which the simulation will be totally steady state. So if you want to save this animation, you can just zoom it using your scroll button, and you can go to file, save animation, and you can type in any file name like velocity plot and make sure it is in MP4. And here for a better quality you can do 2160 by 1080 pixels, and you can select frame rate something around 20 so that it is slightly faster, and you can click on OK to make the animation. Once the animation is done, you can go to the folder where you have saved all of these, and you can refresh to see the video. So here is the video of the simulation where we are getting the velocity plot. So this is how we do a simple foam case for a flow or a prism. I hope you like the video. If you like the video, drop a like, subscribe to the channel. If you have any doubts, you can drop it in the comment section. Thank you.